Today's goal is to simplify rational expressions and classify discontinuities. Remember, rational expressions are ratios of polynomial functions. Expression, again, means there's no equal sign, so it's not an equation or a function. And classify means name a category. So I'm not sure yet what the categories are. We'll get there soon. Discontinuities means not continuous, so places where the function does not continue. Okay, so today we're going to look at rational expressions, that is, ratios of polynomials that don't have equal signs, and we'll classify, give a category for places where the function doesn't continue. Here's the guiding idea. You and your siblings just ate massive pieces of cake. Here's a picture of me and my brother and sister. You had half a cake, your brother says he ate 2/3 of a cake, your sister says she has an even bigger piece of cake. Did anyone eat the same amount of cake? Well, let's take a look. You ate half a cake, and your brother ate 1/3 of cake. Oops, these should be the same size. We'll assume the cake itself is the same size. And your sister ate 4/6 of a piece of cake. Sorry, brother ate 2/3 of a piece of cake. Okay, well, we can tell by looking at these pictures, right? This is sort of a silly example, but the idea is that your brother and sister ate the same amount because 2/3, if you multiply by 2/2, that's because you're making twice as many pieces, is exactly the same as 4/6. But 1/2 is not the same size, right? It looks like you ate less cake than your brother or your sister. 1/2 is not the same as 2/3. So here is the important thing to remember. You can't add or subtract the same number from the numerator and denominator and expect to get the same fraction, right? 1 + 1 is 2, 2 + 1 is 3, but 1/2 and 2/3, these are different sizes of pieces of cake, right? These are totally different fractions. But you can simplify a fraction if numbers are being multiplied by the same number in both the numerator and the denominator. So when we're simplifying a rational expression like this, I cannot say, it would be mathematically illegal to say, cool, 3/-6, that's the same thing as 1/-2, so we're done. Or maybe let's just cancel x's, right? Here's an x, there are 2 of them, so let's reduce this to just a 1 up top and an x on the bottom. Because x and 3 are being added together. You cannot cancel terms that are being added or subtracted. That's illegal math. Doesn't work. Okay, so instead, we'll have to cancel things that are being multiplied. Well, it doesn't look like anything's being multiplied here unless we factor the denominator. Then you've got a product, 2 things being multiplied. You can factor the denominator, in this case, to x + 3 times the quantity x - 2. And of course, we've got x + 3 on top. Now, this is an entire factor. And we're multiplying really nothing up top. So you're multiplying 1 by x + 3 up top. And you're multiplying x + 3 by x - 2 in the denominator. Since you're multiplying the numerator and denominator by x + 3, it's legal to cancel them out. So this reduces to 1 over x - 2, as long as x isn't equal to -3 or 2. X can't be -3 or 2 because those are the values that would make the denominator equal to 0, and it doesn't make sense to divide by 0. So these are your discontinuities, the places where the function does not continue. The discontinuities are x equals -3 and x equals 2. We say x can't be these things because they make the function stop continuing. Okay. In example 2, again, we've got a bunch of terms up top and in the denominator being added or subtracted. You cannot cancel terms that are being added or subtracted. You can only cancel terms that are being multiplied by the numerator and the denominator. So to make this look like a product, we'll factor the numerator and the denominator. But this time, you don't see any of the same factors in the numerator and the denominator. So in fact, this expression cannot be simplified. We can name the discontinuities. X can't be 4 or -3. That is the same thing as saying there are discontinuities at x equals 4 and x equals -3, because you can't divide by 0. But this expression cannot be simplified since there are no factors that you're multiplying by in both the numerator and the denominator. This example is a little bit different because it's asking us to classify the discontinuities. Again, classify means you got to name what categories are possible. In order to know what the discontinuities are, you have to know what values would make the denominator equal to 0. That was easy to tell once we factored, because then you just look at each individual factor. What would make this equal to 0? 4. What would make this equal to 0? -3. So if you have 4 here, you've got a 0 times something. That would make your whole denominator 0. If you have a -3 here, you have -3 plus 3 is 0. 0 times something would make your denominator equal to 0. So to find discontinuities, we have to factor the denominator and examine what numbers would make the denominator equal to 0. So in A, for f of x, we can write this function as in factored form. And then it's easy to see the discontinuities are x equals 0 and x equals 5. Those are the two values that make the denominator equal to 0. Now, if we're simplifying, we see that we've got an x up top and x on the bottom. And this x is really being multiplied by -1. This x is being multiplied by 5 minus x. That's why we're allowed to cancel them. So this function is almost identical to the function -1 over 5 minus x, except at x equals 0 and x equals 5. X equals 0 is called a removable discontinuity. That's one category. One possible type of discontinuity is removable because it appears as though we removed its factor from the expression when we simplified. X equals 5 is the other kind of discontinuity. It's a vertical asymptote. There are only two types of discontinuities of rational functions. And x equals 5 is a vertical asymptote because it did not get removed when we simplified the function. Okay, let's take a look at g. G of x is, once we factor it, and we're factoring so that we know what the discontinuities are. And so we can see if any of the factors get removed, therefore producing removable discontinuities. Yep, indeed, we see that the factor x minus 5 cancels out because we're multiplying both the numerator and the denominator by the factor x minus 5. So x equals 5 is a removable discontinuity. And x equals -1 is the other kind. It's a vertical asymptote. That's it. Well, it's helpful to have the graphs here because then we can tell algebraically or graphically what these discontinuities look like. Take a look at the graph of f. We can see that there's a break in the graph at 5, right? We can see this discontinuity, this break in the continuity. Like if you were to graph the function yourself or trace over it, you'd have to pick up your pen between these two sections. So x equals 5 is really visible, but at x equals 0, you don't see anything happening. That's because if you were to zoom all the way in, there's a single point missing where x equals 0. It looks like a hole in the graph, but one point is so small you can't see it with your naked eye. If you were to look at a table of f on your calculator, when you get to the x value 0, it'll say error. It'll also say error at 5, whereas at every other point it's going to give you some y value, right? So we can see that these are discontinuities, but what it actually looks like on the graph of the function depends on if you're dealing with a removable discontinuity, that is a hole, a single point missing that has been removed from the function, or a vertical asymptote. So the same is true in b, right, this function, sorry, I've been calling it g of x, we can see this break this gap at x equals -1, but you can't see the hole missing at 5 because a point is too small to be seen with the naked eye.